This note is on isotopic abundance, and so we'll go through and take a look at how we deal with these types of reactions. For the most part, when we look at different elements on the periodic table, we find that they have slightly different masses. And this has to do with the fact that what makes up the mass of a particular atom is essentially the number of protons and the number of neutrons. Now, the number of protons defines what that particular element is going to be. The number of neutrons essentially adds to the stability of the element. So if there's a weird number of neutrons that don't really fit into the nucleus, then the element becomes unstable or radioactive. If the number of neutrons fits in there nicely, then we have a stable element. And the different ways the neutrons can fit into that nucleus allows for different, what we call isotopes. So when you have the same element with a slight variation in the mass, in other words, a different number of neutrons, then that is called an isotope of that element. And most elements have quite a few isotopes. Now, the mass number is based on the sum of the number of protons and the number of neutrons in the nucleus. And the average atomic mass is the average of all the isotopes of that particular element. When we look at kind of how that breaks down, we call that the relative abundance. And the relative abundance of a particular isotope really depends on what percentage of a large sample is that particular isotope. So we have the average atomic mass that equals the average mass of all the elements in the of that particular element's isotopes. And the way we calculate that, we simply take the atomic mass of isotope A and we multiply it by its relative abundance. And we add to that the atomic mass of isotope B multiplied by its relative abundance, and C and D, and if there's any more, we add those in there too. So, as an example, let's go through argon. Argon contains 99.160% argon-40, 0.34% argon-36, and 0.06% argon-38. So to go through this calculation then, we would, to figure out the average atomic mass of argon, we would calculate it in this way. So 40 essentially is the mass number for argon-40 times its relative abundance. So as a percentage, it's changed to a decimal. So 99.160% becomes 0.99160. And then argon-36 times its percentage, 0.0034. And argon-38, so 38 times 0.0006. And if you plug that into your calculator, you get 39.98 atomic mass units. All right, another example. Boron exists at 2 naturally occurring isotopes. Now, if we were to do this calculation backwards, so let's say we have some boron-10. It has an atomic mass of 10.01 atomic mass units. The reason the numbers are different is because we can get more precise values today. And so in defining it, if I give you a more precise mass of a particular isotope, then that's what you would use. In this case, the 10.01 atomic mass units. And boron-11 then has an atomic mass of 11.01 atomic mass units. So to determine the relative abundance of each of the isotopes, we need to assume we have a sample, let's say, of 100% or 1. And then if we let X be the relative abundance of B boron-10 in this case, just pick one, doesn't matter which one. Then 1 minus X is the relative abundance of boron 11. All right, so 1 is the whole, and X is the part that's boron 10. So the whole minus X is the relative abundance of boron 11. Okay, so that's how that works. So then we plug the numbers into our equation, which is the average atomic mass, the 10.81 atomic mass units that we get from our periodic table. So if you look that up, that's what you get, is equal to 10.01, the mass of boron 10, times its relative abundance, X. And we add to that the mass of boron 11, 11.01 atomic mass units, times 1 minus X, its relative abundance. And so then we expand the brackets, collect like terms, bring the X to one side, the numbers to the other side. So X is equal to 0.2. And so 1 minus X is going to be 0.8. And so that means that boron 10 has an abundance of 20% and boron 11 has an abundance of 80%. All right, so there's the homework for the abundance. We'll get you to try those questions, come to class then with questions and issues about any of those calculations.